All right, so get ready, because today we're going deep into the world of topological qubits. It's a really fascinating area of quantum computing.
Yeah, it's not just like new hardware or anything. It could change how we think about quantum computation entirely.
Exactly. Now, I know our listeners are pretty savvy, but let's do like a super quick recap for anyone just tuning in. Qubits, as most of you probably know, are what quantum computers are made of.
Yeah.
And they're not like the bits in your laptop, which can only be like a 0 or a 1. Qubits, they can be in superposition, which basically means they can be both 0 and 1 at the same time.
Right, and that's where the real power comes from. That ability to be in so many states at once means quantum computers can do calculations way faster. But one problem with qubits is that they are really sensitive. Even the smallest change can cause errors.
And that's where topological qubits come in. They're like the superheroes of the quantum world. And Jorgo Schneppet, who wrote the essay we're looking at today, he really emphasizes this. Topological qubits are incredibly stable. It's like they have this built-in shield protecting them from the noise of the quantum world.
That's a great way to put it. And the secret to that stability is topology. I know it sounds kind of intimidating, but at its core, topology is all about shapes. It's the study of how shapes can change without actually changing their fundamental properties.
So like if you stretch a rubber band, it's still a rubber band.
Exactly. And that same concept applies to topological qubits. Instead of a rubber band, imagine these tiny particles called anyons. They exist in this like two-dimensional world, and the way they're arranged, their knottedness or braiding, that's where the information is stored.
So it's not about the state of a single particle, but the way all these anyons are linked together.
Precisely. And because that information is in the overall structure, it's super resistant to any local disturbances. Think of it like the difference between writing on a whiteboard, which you can easily erase, versus like carving something into stone.
That's such a great way to put it. And Schneppet really hits on this in his essay. He's saying that this stability could totally change the game. Topological qubits could be way more efficient than regular qubits.
Exactly. This means we wouldn't need to spend as much energy correcting errors. And we could focus on building bigger and more powerful quantum computers.
Okay, I'm starting to understand why everyone's so excited about topological qubits. But can we talk about those anyons for a second? They sound like something out of Star Trek. Can you give us like the simple version of what they are?
Sure, so they're pretty unique. Anyons are particles that can only exist in two-dimensional systems. And the really cool thing is that the way they move around each other, the way they're braided, that's what actually does the calculations.
Wait, so the anyons are like dancing, and that's how they compute. That's wild.
It is, and Schneppet talks about this special type of anyon called Majorana fermions. They're really interesting for building topological qubits.
Ah, Majorana fermions. Yeah, I've heard about those. What makes them so special?
Well, Jorgo Schneppet points out that they are their own antiparticles. It's a bit of a mind bender, but basically it means that if a Majorana fermion meets its antiparticle, they annihilate each other. But because they're both the particle and the antiparticle at the same time, they can make extremely stable qubits.
Okay, I'm about to think about that one for a minute. But it sounds like these Majorana fermions are a pretty big deal for topological qubits.
Oh, absolutely. In fact, Microsoft has this initiative called Station Q, and they're pouring tons of resources into researching Majorana fermions. They think Majorana fermions could be the future of quantum computers.
So it seems like we're at this point where we've discovered this amazing new tool, but we're still figuring out how to use it. Like we've found this new language, but we don't know the alphabet yet.
That's a great analogy. And like any new technology, there are going to be challenges along the way.
Right. So before we get too deep into the how, I think it's important to make sure our listeners understand. This stability we keep talking about, it's not just a cool feature. It's a huge deal.
You're right. It all comes down to this. Regular qubits are so sensitive to their environment that they lose information really quickly. It's called decoherence, and it means you need these really complex systems to keep them working properly.
It's like, I don't know, trying to write on a piece of paper while you're in a hurricane.
Yeah, exactly. But topological qubits, because the information is in their topology, they're much more resistant to that kind of noise.
So it's like if regular qubits are writing in the sand, topological qubits are carving into granite.
Exactly. And that could mean using way less energy, fewer resources fighting errors, and ultimately a much easier path to building larger and more powerful quantum computers.
Okay, I think our listeners are starting to get why everyone's so excited about topological qubits. But of course, there are always challenges with groundbreaking technology, right?
Oh, absolutely. And Schneppet is very upfront about that in his essay. There are some pretty significant hurdles we need to overcome.
Okay, well, let's dive into those after a quick break. We'll be back in a moment to explore the other side of this fascinating coin. Okay, so we've been talking about how amazing topological qubits are, this incredible potential for stability, all thanks to this crazy thing called topology and these weird ennions. But Yurgo Schneppet, he's also really clear in his essay that there are some big challenges, like some serious roadblocks before we start seeing topological qubits in our phones and laptops.
Yeah, definitely. And I think it's important to understand these challenges because it shows you just how much work is going into this research. I mean, it's mind-blowing.
So let's get into it. What are some of the biggest challenges facing the development of topological qubits?
Well, one of the biggest ones, one of the most fundamental challenges is actually creating the ennions, especially those Majorana fermions, the ones that seem to have the most potential. They're really hard to make.
We were talking before about how they only exist in 2 dimensions, right?
Right.
And they need these really specific, precise conditions.
Exactly. It's like imagine trying to manipulate individual atoms on a surface. And you have to keep the temperature just barely above absolute zero. I mean, the level of engineering and scientific precision is just insane.
It's like, I don't know, doing surgery on a single cell with chopsticks in the middle of a blizzard.
That's a pretty good analogy. It really is that complex. Even the tiniest change in temperature, a random magnetic field, anything like that, it can totally mess things up.
So it's not just about building the right hardware, it's about having this insane level of control. I remember Schneppet mentioning that researchers are using magnetic fields to try to manipulate these ennions.
Yeah, so it's kind of like they're creating these tiny racetracks for the ennions using magnetic fields. They carefully calibrate the shape and the strength of those magnetic fields to guide the ennions, and they're hoping to use that to control the braiding, because that's what actually does the quantum computing.
So it's like a quantum ballet, right? These tiny dancers moving around on a stage we can't even see. But even if we figure out how to create these ennions and make them dance for us, how do we actually read the results? They don't just like spit out a number on a screen.
Right, and that brings us to another huge challenge. Measurement. Because all of this is happening in this 2-dimensional world, it's super hard to actually see what's going on. So we have to come up with really clever ways to extract the information.
It's like trying to understand a conversation happening in a soundproof room.
Exactly, and Schneppet talks about this in his essay. Researchers are trying to measure tiny changes in the electrical properties of the material. It's extremely sensitive work. They need incredibly precise instruments and really sophisticated analysis. It's like trying to hear a whisper during a hurricane, but they're making progress.
It's really incredible the amount of ingenuity that's going into this research.
Sure.
But let's talk about scalability for a second. Right now we're talking about controlling just a few of these ennions. But for a quantum computer to actually be useful, we need thousands, maybe even millions of them.
And that's another big point that Schneppet makes. Scaling up is a major challenge for any type of quantum computer, but it's especially difficult for topological qubits.
Oh, how come? Is it just about building more of those tiny racetracks for the ennions?
It's way more complicated than that, you see. As you add more qubits, they start interacting with each other, and those interactions can be really complex and unpredictable. So you have more potential for errors, and it gets exponentially harder to control everything. It's like trying to conduct an orchestra with 1 million musicians all playing slightly different tunes.
Wow, that's a great analogy. So it's not just about making more qubits, it's about making them all work together. And I imagine that's a huge engineering challenge.
Yeah, for sure. And on top of that, you have to maintain those super precise conditions for the ennions to even exist, which gets way harder as the system gets bigger.
It sounds like building a topological quantum computer is kind of like trying to build a skyscraper out of snowflakes.
You could say that. It's an incredibly difficult task, and that's why we need to be realistic about the timeline.
Yeah, because as exciting as this technology is, we don't want to overhype it. What does Schneppet think? Where does he see this research heading in the near future?
Well, he says that small-scale prototypes, maybe with a few dozen qubits, could be possible within the next 5 to 10 years. But for larger, more powerful systems, the kind that could really revolutionize things, those are probably further out, maybe 15 to 20 years, or even longer.
So there's a long road ahead, but there's so much potential, it's definitely worth the wait, wouldn't you say?
Absolutely. I mean, think about what we could do, revolutionizing medicine, materials, science, cryptography. It's an incredible future that we're working toward.
Okay, so we've talked about the why, we've talked about the how, but let's talk about the who for a second. Schneppet mentions some of the leading research groups in this field. Can you tell us a little bit about them?
Yeah, so we already mentioned Microsoft's Station Q initiative. They're one of the biggest players in the field. They're really focused on Majorana fermions and building topological qubits, but there are also a lot of universities doing amazing work in this area.
Like who? Any specific ones come to mind?
Well, the Weizmann Institute of Science in Israel, they're a major hub for topological quantum computing research. They've made some really important contributions to understanding how anyons work.
And I've also heard about some cool stuff happening at TU Delft in the Netherlands, right?
Yep, TU Delft is another powerhouse. They're doing some cutting-edge research on new materials and new techniques for creating and controlling those Majorana fermions.
It's really amazing to see this kind of global effort to figure out topological quantum computing.
It really is. And what's really cool is how interdisciplinary it is. It's not just physicists working on this. You have material scientists, computer scientists, engineers, even mathematicians. It's a really collaborative field.
It's like a scientific symphony orchestra, everyone bringing their own expertise to create something truly amazing.
That's a beautiful way to put it. It really shows the complexity of this challenge.
And it reminds us that even though we're focusing on this one specific area of research, it's connected to so much more.
Exactly. And that's what makes it so fascinating. All the connections, the collaborations, and the potential for discoveries that could impact so many different fields.
You know, what I find so exciting about this field is that it's not just about building better computers. It's about understanding the universe at a deeper level. We're talking about exploring the fabric of reality.
I totally agree. There's this sense of wonder, this pursuit of knowledge that's driving so much of this research.
And it's a journey that we're all on. Every time we talk about these ideas, every time we learn something new, we're contributing to this collective effort to understand the universe.
So as we wrap up this part of our conversation, I want our listeners to take a moment to think about all of this. The potential, the challenges, the sheer audacity of what we're trying to do.
And in our final segment, we're going to come back to a question that Schneepat asks in his essay. It's a question that makes us really think about the possibilities, the future that this technology could unlock. Okay, so we've spent a lot of time talking about all the details of topological qubits, how they work, the challenges and all that. But you know what I think is really exciting? Yorgo Schneepat, he asked this question in his essay. What scientific breakthrough in this field would really blow our minds?
Yeah, it's a great question. It really gets you thinking about the possibilities, you know. For me, it comes back to what we were talking about before, the power of simulating complex systems. Like, imagine if we could actually see into the quantum world, understand how molecules behave at the most basic level. Think about what that would mean for medicine, for drug discovery. We could design drugs with atomic precision, no more guesswork, just boom, breakthroughs left and right.
It'd be like having this quantum microscope, right?
Yeah.
Seeing the atoms dancing around and then being able to just, I don't know, build materials from scratch with total control. It's pretty mind-blowing. What about you? What kind of breakthrough gets you the most excited?
That's a tough one. There's so much potential. But I think for me, it's the impact on artificial intelligence. Imagine AI algorithms running on topological quantum computers. They could process information at speeds we can't even comprehend right now. We could solve problems that are impossible for regular computers. It'd be a total paradigm shift.
Yeah, that's amazing to think about, but also kind of scary, right? Like, what happens when AI becomes that intelligent? It could solve all our problems, or it could, decide it doesn't need us anymore.
Right. There are definitely some big ethical questions we need to consider. But for now, I think it's okay to just be excited about the possibilities. It's incredible what humans can achieve when we put our minds to it.
It really is. It's like we're on the verge of this whole new era, a quantum renaissance, where everything we know about computing is about to change. And Schneepat makes a good point. It's not just about the end goal. It's about the journey, too. All the discoveries we make along the way, those are just as important.
Absolutely. Every experiment, every new theory, it all adds to our understanding of the universe. It's a testament to human curiosity, We always want to know more, push the boundaries further.
And it's not just one person. It's this global effort. All these scientists all over the world working together to unlock the secrets of the quantum realm. It's pretty inspiring.
It is. It makes you realize that even though we're focusing on this one specific thing, topological qubits, it's part of something much bigger.
Exactly. And that's what I love about these deep dives. It's a chance to step back and look at the bigger picture, to see how everything is connected.
So, to our listeners, as you're going about your day, think about those tiny anyons braiding their way into the future. They might seem small, but they have the potential to change the world.
Maybe you'll be inspired to learn more about quantum computing, or even contribute to the research yourself. Who knows? You might be the one to make the next big breakthrough.
The future is full of possibilities, and it's up to us to shape it.
So keep exploring, keep asking questions, and most importantly, keep that curiosity alive. Until next time.